Hello and welcome. In the last session, we discussed the fundamental theorem of arithmetic, which is the most important result in elementary number theory, probably after Besso's identity. Fundamental theorem of arithmetic guarantees that given any integer n greater than or equal to 2, it is either a prime or product of primes, and the primes appearing in this product is unique up to reordering of the primes. We are going to see a few consequences of the fundamental theorem of arithmetic in this session. Note that fundamental theorem says that any integer is a product of primes, and therefore primes are the basic building blocks of natural numbers. This is one of the reasons why prime numbers are named as prime numbers, in the sense that they are most important among natural numbers in building all the natural numbers. So the topic of our discussion today is fundamental theorem of arithmetic and its consequences, applications. Recall that fundamental theorem of arithmetic states that given any integer greater than or equal to 2, either n is a prime or there exist unique primes, p1, p2, etc., pk, such that n is the product of all these primes. Now, according to our version of fundamental theorem, we are not asking for the primes p1, p2, etc. to be unique or distinct, not unique, distinct. So p1, p2, etc., some of them may be equal. Now suppose that we collect all equal primes, all the primes that are equal, and we raise the power of prime to corresponding to the number of appearances of each and every prime in the form that p1 raised to a1, etc., pr raised to ar. Then p1, p2, etc., pr are distinct. Just see that what we did is we collected same primes together, and suppose that p1 is appearing 3 times, therefore we will write p1 raised to 3. Suppose p2 is appearing 2 times, we will write p2 raised to 2, etc. Suppose that pr is the last distinct prime appearing, so pr raised to ar. If ar is the number of times pr is appearing in n. So we collect all the primes together, club them together, and write it in the power. So this expression is known as prime power decomposition of n. So prime power decomposition of an integer is the way in which we have to write n as a product of power of primes in such a way that each and every prime is appearing exactly once. Now suppose that we put the extra condition that n is equal to p1 raised to a1, etc., pr raised to ar with ai greater than or equal to 1, and suppose we put the extra condition that p1 less than p2 less than etc. less than pr, that means the primes are arranged in the increasing order, then this representation of n as a product of prime powers is known as canonical decomposition of n. So the difference between canonical decomposition and prime decomposition is that in, of course, both these representations we need the primes to be unique and the powers to be positive, but in canonical decomposition we want in addition that the primes are arranged in the increasing order of size. So p1 is strictly less than p2, p2 is strictly less than p3, etc. pr is the largest prime that's appearing towards the end. So we will see some quick examples. So we are going to find out the prime decomposition of 60 and of course canonical canonical decomposition of 60 we are going to find. So we know that 60 we can write as if we try to split it, it's going to be, see, in whatever way we need to, we wish we can split it, and one possibility is 15 into 4. We know that this is, now 15 can be further factorized into 3 into 5 into 4 can be factorized 2 into 2. Now suppose that we write in the increasing order of magnitude. So 2 into 2, therefore 2 appears twice, therefore this is 2 square, 3 to the power 1, 5 to the power 1. This is the canonical decomposition of 60. That is 2 square into 3 to the power 1 into 5 to the power 1. Okay, one more example. 2520. Find the canonical decomposition of this number. Okay, 2520, if we carefully look at this, we can see that this is a multiple of 10. So probably we can write it as 252 into 10. Now 252, we can see that 2 plus 5, that's 7 plus 2, 9. Therefore this is a multiple of 3. So this is 3 into, in whatever way we like, we can split it. We can factorize it. 3 into 84 into 10. Now we will break it down further into primes. 3 into 84. 84, we know that it is 12 into 7. 12 into 7 into 10. And this is again equal to 12 into 3 into 12. We can write as 2 square into 3 into 7 into 10. We can write as 2 into 5. Now we start arranging them in the increasing order, beginning from the least prime, that is 2, and 2 square is, so 2 square and 2, therefore 2 cube. Now 3 square, now next prime is 5 to the power 1, now 7 to the power 1. This is the canonical decomposition of 2520. Now we are going to see a consequence of fundamental theorem of arithmetic. Suppose that this is an observation. Suppose that we have the canonical decomposition of n in the following way: p1 raised to a1, etc., pk raised to ak. Now suppose d is a divisor of n. Then d will be possibly having, d may have some prime factors, and suppose p is a prime dividing such that p divides d. Therefore by the transitivity of divisibility, p divides d and d divides n implies that p divides n, implies that p divides pi raised to ai for some pi. So what we are basically, and not only that, also the power of p in d must be less than or equal to ai. That's obvious because we know that if p divides pi, and therefore definitely p is going to be equal to pi, because we know that if a prime is dividing the power of another prime, p divides pi implies pi raised to ai implies that p divides pi into pi ai times. Therefore p must divide pi. So p divides pi, p and pi are both primes, therefore p must be equal to pi. Not only that, the power of p in d, so if p is appearing some b times or bi times, so that bi must be less than or equal to ai. That is, if p to the power bi divides d, then bi must be less than or equal to a. That's also there. So the final conclusion is the following. So to find out all the divisors of n, we need to only take all the primes in n and take all possible powers of those primes appearing in n from the least to the maximum. That is, any divisor of n looks like the following way: p1 raised to b1, p2 raised to b2, etc. pk d equal to pk raised to bk. But one important thing is here, this is not actually the prime factorization or canonical decomposition. Here is one possibility. So all these pi's need not appear in each and every divisor. Some of the pi's may be absent in this D, and therefore to accommodate that possibility also we will allow bi to be 0. So bi is greater than or equal to 0, and it is less than or equal to ai, where a is the power of pi appearing in this n. So to find out all the divisors of pi, what do we need to do now? So we need to vary b1, b2, b3, etc. between 0 and ai, and for corresponding to each and every choice of bi, we will be getting different divisors. So that is the conclusion of this discussion. Now we are going to apply this in the following problem. So the question is the following: find all positive factors or divisors. Factor, divisor, both means same for us, of the number 60. So to find the divisors, as we have just observed, we will write down the prime fact canonical decomposition of 60 first. But we know already that the canonical decomposition is 2 square 3 1 5 1. Okay, this is equal to 2 square 3 to the power 1 5 to the power 1. Therefore if d divides 60, then d looks like then d is of the form d equal to 2 to the power b1, 3 to the power b2, 5 to the power b3, where 0 less than or equal to b1 less than or equal to a1, which is 2, and 0 less than or equal to b2 less than or equal to 1, and 0 less than or equal to b3 less than or equal to 1. So what are now the possibilities? So if we keep on varying this b1, b2, b3 among 0 to 1, 0, 0 to 2, 0 to 1, 0 to 1, then we will get the divisors in the following way. The possibilities are the following. So we start with the least: 2 raised to 0, 3 raised to 0, 5 raised to 0, this is equal to 1. Now we are going to take various other possibilities. Now we are going to increase the value of the power of 2 first. So 2 raised to 1, 3 raised to 0, 5 raised to 0, that is equal to d. These are the possibilities. So this is equal to 2. Now we will increase once again: 2 square 3 0 5 0, this is equal to 4. Now we again come back: 2 to the power 0, 3 to the power 1, 5 to the power 0, this is just 3. Now 2 to the power 0, is there any other power for 3? There is no other power, because 3 can have at most. So we will increase the value of power of 2, 2 to the power 1, 3 to the power 1, 5 to the power 0, which is 6, and we keep on doing like this. And without even calculating all these, so I'm leaving this as an exercise to find remaining factors. I'm just leaving this as an exercise by taking various possibilities for this powers of 2, 3 and 5. But even without going through all these divisors, we will be able to say how many factors are there. How do we do that? We know that 2 has 3 possibilities: 2 to the power 0, 2 to the power 1, 2 to the power 2. Therefore there are 3 possibilities for powers of 2 to appear in the product. Now for the powers of 3 to appear: 3 to 0, 3 to 1, therefore there are 2 possibilities. Now for powers of 5, 5 to the 0, 5 to 1, there are 2 possibilities. Therefore altogether there are 3 into 2 into 2, 3 into 2 into 2, that is equal to 12 possibilities. Therefore 60 has altogether 12 divisors or 12 factors. We need not actually find all the factors to arrive at to find out the number of divisors of 60. In fact, from the previous problem, the way in which we found out the number of divisors without finding all the divisors, we can actually make a general statement. So the general observation or statement is the following. Suppose that n has the canonical decomposition n equal to p1 raised to a1 etc. pk raised to ak, where this is the canonical decomposition. Suppose now every divisor will be of the form p1 raised to p1 etc. pk raised to pk with the condition that 0 less than or equal to bi less than or equal to ai. Now for this bi, the possibility, each bi, the possibility is that 0, it can be 0, it can be 1, it can be 2 etc. up to ai. Therefore there are ai plus 1 possibilities for various possibilities for the to become the power of p1. So similarly for that is for p1 there are a1 plus 1 possibilities, p2 there are as powers, a2 plus 1 possibilities etc. pk has ak plus 1 possibilities. Therefore all together, so the total number of divisors is the total number of possibilities, which is a1 plus 1, a2 plus 1 etc. ak plus 1. Therefore this is equal to a1 plus 1 into a2 plus 1 into etc. ak plus 1. So this is the number of divisors of the number n, and this is obtained from the canonical decomposition of n. So to find out the number of divisors, it is not necessary to list all the divisors, but we need to just find out the powers of primes appearing in the largest power of each prime appearing in the canonical decomposition, add 1 to it, because we are allowing the possibilities that that prime may not appear, or the power, the prime raised to 0 may appear in that divisor. So taking that possibility also, we will see that a1 plus 1 is the number of ways in which p1 can appear in D, and taking like that, the total number of possibilities of pi's appearing in D is a1 plus 1 into a2 plus 1 into etc. ak plus 1. So we can find the number of divisors in this way. Now we have a question using the observation previously. Find the number of divisors of the number 2520. See, we will use the prime factorization, the canonical decomposition, and the canonical decomposition is 2 cube 3 square 5 7. So 2 cube 3 square 5 1 7. Therefore number of divisors is equal to, as per our observation, this is 3 plus 1 into 2 plus 1 into 1 plus 1 into 1 plus 1. This is 4 into 3 into 2 into 2, which is nothing but 48. So 2520 has 48 positive divisors, including 1 of course, and the number itself. And now we have slightly different problem which is more interesting. So the question is, it looks a little bit tricky. So the question is the following: find the number of trailing zeros in 234 factorial. That means that how many zeros are there towards the end of 234 factorial. Can we say that at least 1 0 is there? Definitely, because we know that 234 is equal to 1 into 2 into 3 4 5 etc. the product of all numbers up to 234. Definitely 2 into 5 is appearing, therefore at least a 10 is there, therefore at least one 0 is there, that's guaranteed. So zeros are guaranteed because there are 2's and 5's in 234 factorial. Now, how to find out all the number of zeros, or how many multiples of 10 are there in 234 is what we have to find. So we know that if 10, we need to find how many tens or the largest power of 10 dividing this. So but we know that 10 is nothing but this is equal to 2 into 5, and if we can find how many pairs of 2, 5 can be taken from prime factorization, not canonical decomposition, prime factorization of 2, 3, 4 factorial, then those many zeros will be there. So suppose that there are some 5 2's and 5 5's appearing in this product. So 5 2's and 5 5's in the form, in the sense that, see here we have 4 here. This 4 consists of 2 2's. Now we have 10 here. 10 consists of 1 2 and 1 5. Now 15 is there. 15 consists of 1 5. So like that we have to find out how many 5's are appearing in 234 factorial and how many 2's are appearing. So basically what we are looking at is if we are able to write 234 equal to 2 to the power a into 5 to the power b into whatever is remaining as c, then we know how many 2's are there, how many 5's are there. Okay, so if we can find out how many 2's are there and how many 5's are there, then probably we can say, so find out how many 2's or how many 2's and how many 5's in this decomposition. This is not actually the prime decomposition or canonical decomposition. Here we are just considering the powers of 2 and 5 alone. Now one more thing, to make up a pair of 2 and 5, suppose that 2 has some 15 pair and 5 has some 20 pair. Sorry, 2 has the power 2 to the power a is 2 to the power 15 and 5 to the power b is 20. Suppose 2 to the power, we don't know exactly what it is, 2 to the power, of course 2, we can expect 2 to the power to be something more, 2 to the power 10 and 5 to the power 7. Then how many pairs of 2 and 5 we can take? We can take 2 5 pair. So 2 5 2 5 2 5, we can take at most 7 pairs. So number of 2 5 pair, this is going to be equal to least of AB, minimum of AB, because if B is more, it's useless because we need those many A's to make a pair. So we need to only consider the largest, we need to only consider the minimum of A and B only we need to consider, and those many only pairs will be appearing in 234 factorial. And one more observation probably is that 5 is more than 2 and 5 is much more than 2, because within 5 itself we will be getting 2 and 4, therefore 4 2's are there. So we can naturally expect that number of 2's is going to be much more. So obviously A is going to be greater than or equal to, in fact A is going to be greater than or equal to B. So the number of zeros or number of tens is equal to number of how many pairs we can make at most B. That is the largest power of 5 appearing in this. Now to find out the largest power of 5 appearing in this factorization, 2, 3, 4 factorial is equal to, okay, this is 2, 3, 4 factorial, not 2, 3, 4, equal to 2 to the power A, 5 to the power B and C. Remember that, so every multiple of 5 will contribute at least once to 234 factorial. So first observation, every multiple of 5 contributes at least 5 to 234 factorial. So what are those numbers? So there is 5 is there, 10 is there, 15 is there, 20 is there, etc. Now how many multiples of 5 are there up to 234? So in 234 factorial, how many 5s will be there? So number of 5s till 234. See that 234 factorial is made of 1 into 2 into 3 into etc. all the numbers up to 234. So to find number of 5 multiples, not 5s, this is 5 number of 5 multiples till 234, we need to just find the floor of 234 by 5, that is equal to 46. Okay, because 46 into 5 is going to be equal to 230. Now another observation probably we have to make here, 5 square or multiples of 5 square, multiples of 5 square contributes an extra 5 in 234 factorial. That means, for example, suppose that 25, already 1 5 we have already counted. Now one more 5 is there, one extra 5. So one more 5 is there, therefore each multiple of 25 will contribute another 5 in addition to the already counted 5 to 234 factorial. Now how many multiples of 25 are there? Multiples of 25 in 234 factorial is the floor of 234 by 25, and this is equal to 9. Now multiples of, we cannot stop here, multiples of 5 cube, that is equal to 125, that contributes an extra 5, one more 5 in addition to whatever is contributed by 5 and 25. So multiples of 125 in 234 factorial, that is easy to compute because there is only one 125 multiple, which is 125 itself, therefore this is 1. So the next power of 5 is 5 to the power 4, that is going to be above 234, therefore we need not consider that. So now we have 5 contributions are coming from 1 5 contributed by every multiple of 5, therefore there are how many are there? There are 43 of them, there are 46 of them. Now another extra 5 is contributed by multiples of 25 and they are 9 in number, and now we have one more 5 contributed by multiples of 125. Unfortunately there is only 1, and so to find out the number of 5s appearing in 234 factorial, we need to add all these things. So 46 plus 9 plus 1, we are going to add all these things. Therefore, total number of 5s in 234 factorial is equal to 234 by 5 the floor of it plus 234 by 25 the floor of it plus 234 by 125 the floor of it. We have already counted these things, so this is 46 plus 9 plus 1 and this is equal to 56. Therefore, there are 56 5s in 234 factorial, and number of 2's will be definitely more than this 56, because if we count the number of 2's without even considering the powers of 2 and 2 multiples in 234 factorial, this is equal to 234 by 2 the floor of it, but this itself is 117. This is greater than 56. Therefore, number of 2 5 pairs in 234 factorial equal to number of 10s in 234 factorial, or 10s dividing 234 factorial. This is equal to 56. Therefore, 234 factorial has 56 trailing zeros in it. So we computed the number of trailing zeros in 234 factorial to be 56. Now we are going to make an observation from this problem. See that we found out the number of 5's appearing in 234 factorial, and in fact we found out the number of 5 multiples appearing first, and after that 5 square multiples, and after that 5 cube multiples, and altogether we added and we actually got the B where 234 factorial is equal to 2 to the power a, 5 to the power b into c. Therefore, we in fact found the largest power of 5 dividing 234 factorial. So, for finding the largest power of 5 dividing 234 factorial, what we did is we found the floor of 234 by 5, the first power of 5, first possible power that is included in 234, next 234 by 25, the floor of it, and after that 234 by 125, the floor of it, that is the largest power of this is 234, not 235. The largest power of 5 appearing in 234, 5 appearing before 234 is 125. So we took the floor of that also. So the observation that we are going to make is the following. So the observation is this from this problem. Let P be a prime such that P divides n, then the largest power of P appearing in or dividing, not appearing, dividing. Appearing in means as in the previous case it's 125. We are not going to derive that thing. The largest power of P dividing 234, not 234, n factorial is equal to, how did we find that? So n by P, the floor of that, plus n by P square, the floor of it, plus n by P cube, the floor of it, plus etc. And this is a finite sum because we know that when the powers of p are increasing, it will definitely exceed n at a stage, and after that the floor will be just 0. Therefore this is a finite sum. This is a finite sum. So to find out the largest power of p dividing n factorial, we need to just take n by p, the floor of it, n by p square, the floor, n by p cube, etc. Until the floor becomes 0, we need to find out all these floors and add them up, and that will be the largest power of p dividing n factorial. Now using this, we have the following exercise, quite easy. Find the highest power of this is an exercise 3 dividing 100 factorial. This is an exercise. One more. Find the number of trailing zeros in 100 factorial, and one more question, 376 factorial. These are two randomly chosen, so this is also left as an exercise. Now we are going to see another application of the fundamental theorem of arithmetic. It's the following. So fundamental theorem of arithmetic can be actually used, in fact the canonical decomposition can be used to find out GCD of two numbers. Finding GCD using canonical decomposition. So suppose that A and B have the canonical decomposition the following way: P1 raised to A1, P2 raised to A2, etc. Pk raised to Ak. Now suppose B is having the canonical. Now this is not actually, okay, we will clarify that. Of course P, A and B need not have the same primes appearing in both these integers, so we will just write P2 to the power P1 to P1, P2 B2, etc. Pk Bk, where Ai's are greater than or equal to 0 and Bi's are greater than or equal to 0. A and B consisting of same primes. So for example, suppose that we consider the two numbers A equal to 12, this is equal to 2 square into 3, and suppose B is equal to 15 equal to 3 into 5. So to make it look like this A and B, we will rewrite in the following way to match the primes in both these numbers. So we will write A is equal to 2 square 3 raised to 1 into 5 to the power 0. So whatever prime is there in B and that is not in A, we will just put that prime to the power 0. Similarly in B, so 2, there is no 2 factor in 2 prime in B, therefore we will write 2 to the power 0, 3 to the power 1, 5 to the power 1. So the GCD of A and B, in this case, we know that GCD divides both A and B and it is the largest divisor of A and B. So if D divides A, it will be having, so we will clarify that first instead of writing this. So if D divides A, if D is a number dividing A, then D will look like P1 raised to D1, or otherwise R1, etc. Pk raised to Rk. If D divides B, if D divides A or D divides B, because A and B are having the same equal primes in their representation. But now D divides A means that this Ri must be less than or equal to Ai, and D divides B means that Ri must be less than or equal to Bi, or in general Ri must be less than or equal to both. If you take the minimum, that's definitely that will divide also. So Ri is equal to minimum of Ai Bi. So GCD is the largest. So Ri is less than or equal to minimum of Ai Bi. Now if we want to take D to be the largest common divisor, then D must divide A and D must divide B, and not only that, the power Ri appearing must be the largest possible thing. So if D divides A and D divides B and D is a largest, then Ri must be the largest possible number. So Ri must be equal to, we know that it's less than or equal to minimum of Ai Bi. So the largest value is therefore equal to Ai Bi. Therefore GCD of A and B is equal to P1 raised to minimum of A1 B1 into etc. into Pk raised to minimum of AK Bk. So this is another way of finding the GCD of A and B using the canonical decomposition, and then matching the primes in such a way that if one prime is not appearing in one number, we will put that prime to the power 0 in that particular number. Though finding the canonical decomposition is a little bit difficult in the case of larger numbers, when the canonical decomposition is easy, this way we will be able to find the GCD of two numbers. So we will try to apply it in the following problem. Find the GCD of 48 and 162 using canonical decomposition. So how to do that? We will write the prime factorization. 48 is 6 into 8. Okay, further factorizing, there is 2. So 3 is here. 2 into 3 into 2 cube, that is equal to 2 raised to 4 into 3. Now 162, this is equal to 2 into 81, that is equal to 2 into 9 into 9. 9 into 9 is 3 to the power 4. So we have same primes appearing in both. Therefore GCD equal to 2 to the power minimum of 4 1 equal to 1, minimum of this is 1, this is 1, 1 4 is again 1. Therefore GCD equal to 2 to the power 1, 3 to the power 1, that's equal to 6. And we have seen a few applications and consequences of fundamental theorem, and we finish the discussion of fundamental theorem with this. Thank you.